Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. Okay, welcome to part 2 of Module 4, Machine Learning Fundamentals. So in this part, we're going to answer this interesting question that how do machines actually work? So what is happening inside this black box, this magic box? Then we said that the machine learned the pattern in the data, right? So what do we mean by that? So we already covered lots of concepts in the part 1. So we talked about data, we talked about the model itself, we talked about different performance matrices, and now it's time to talk about the cost function and that optimization process which is happening behind the scene, and it helps us to learn the pattern from the data. So let's look into that one. So Module 4, Machine Learning Fundamentals, Part 2. This is what we covered last time, Part 1. And specifically, if you're not familiar with these concepts, please make sure you watch Part 1 first and then come to the second part. We are finally ready to answer this interesting question of how do machines actually learn. So at a very high level, we know that, imagine this is our machine learning box. We have some inputs, we have the labels, the model learns the patterns and makes some predictions. And at the end of the day, we're going to compare these predictions with each other and then try to optimize the weights and coefficients of the model, that this performance metrics is going to become better and better and better. So in a nutshell, to answer this question, how do machines actually learn is by optimizing or minimizing the cost function. And what is the cost? The difference, the distance between actuals versus predictions. Okay, now let's look at the formal definitions. Okay, so starting by learning. What do we mean by learning? Learning is this process of finding the model's weights and or the value of the parameters and hyperparameter. What is the cost function? Cost function tells us how good or bad the model is at making predictions given a set of parameters and hyperparameters, right? And so each cost function has its own curvature and its own gradients. And the slope of the gradient, well, basically, gradient is the slope, right? The sign of this gradient is going to tell us how we should update the parameters to make the model more accurate. So very naively speaking, imagine this is the parameter of interest that I'm optimizing over. Let's show it with theta. And this is my cost function. Let's show it with j of, it's a function of inputs and theta. And imagine it's very simple, something like this, right? And at each point, I can go ahead and calculate the slope. So here, for example, the slope is positive. If the slope is positive and we're doing a minimization, where should I go, left or right? Yeah, I should go left, right? So I go to the next point, next point, next point, and hopefully I get to the minimum. If I start from here, look at the slope. The slope is negative. So where should I go? To the left or right? The answer is right. So as you can see in this very simple example, we are going in the opposite direction of the sign of the slope, right? And so we're going to formalize it more mathematically. But so in general, there are two most frequently used optimization algorithms, and they are namely called gradient descent and stochastic gradient descent. So let's see what is gradient descent, and later on why we have to extend it and go beyond gradient descent and use something called stochastic gradient descent. All right, so let's start by the gradient descent definition. It's an iterative optimization algorithm, right, for finding the minimum of a function. So we know that no matter how we define the cost function, we want to minimize it, right? And hopefully, as the name suggests, we want to decrease the gradients along the way. Hopefully, we get to a point that the gradient is equal to 0, right? So we start at some random points and take steps proportional to the negative of the gradient, to the opposite direction of the gradient. And here is the mathematical formulation. So we have theta. Theta is our parameter of interest. And then we have alpha. This is what we call the learning rate. What are the magnitude of the steps that we go to the right directions? And then finally, this is our cost function, and this is the gradient of the cost function, right? So again, if I want to show you visually, I have this function, the cost function of x and theta, and then this is my parameter of interest. Imagine this is our very simple cost function. We are assuming that it is continuous and it's very well behaved, right? And then we start from random points. If I start from this random point, then I calculate the gradient. It's a number. Let's say it's +1. It's a number.
I plug this number here in the gradients, and then I multiply it to something called learning rate. Let's say learning rate is 0.5. So alpha multiplied that gradient, this is 0.5. So I get minus 0.5 here, minus 0.5. And imagine your initial value for theta, again, naively speaking, let's say we started from number 4. So we do 4 minus 0.5, we get 3.5. So we get to this point, 3.5. And we keep repeating this process, right? We keep repeating this process, we get to a point that, let's say at this point, this is equal to 2, and the gradient is equal to 0, right? So we say, okay, if I want to optimize the theta, theta is going to be equal to 2 minus my alpha, 0.5, multiply the gradient, which is 0, it's going to be 2. So I will get stuck here. So this is the optimal value. The same story happens if I start from this random point. Again, the slope is going to be now, let's say, minus 1. I need to, and let's say, again, just for the sake of argument, imagine this is point, I don't know, 1 or 0.5, whatever. And then I say, okay, the new theta is going to be 1 minus the learning rate, 0.5, multiply the gradient, which is minus 1. So I'm going to get 1.5. So as you can see, we're going in the opposite direction, 1.5. Again, these are just, I use very simple numbers. In reality, it might be a little different. The steps are not necessarily symmetric, and etc., depending on the size of the shape of the cost function. Okay, hopefully it gives you a sense that how gradient descent at the very high level is working. All right, now let's talk about the choice of learning rate alpha. Well, if this alpha that we're talking about, the learning rate, is too small, what's the problem? The problem is that the gradient descent can be very slow. I want you to focus on this chart. And again, theta versus your loss function. A small learning rate requires many, many updates before reaching the minimum points, right? So for example, we go from here to here, and as you can see, it requires a lot of iteration. And the problem is that each iteration is using the entire train set to update the parameters. And if the train set is millions of records of data, so and if the model requires so many of these iterations to get to the minimum point, as you can see, it's going to be computationally expensive, right? On the other hand, if the alpha is too large, then the gradient descent can even diverge. We say it can jump over the minimum, or it can even diverge. So let's say, let me show you an example that it can jump. So for example, we start from here, and then imagine alpha is very large, and instead of going this way, we go this way. So we pass the minimum, right? We pass the minimum, and this is a problem. And sometimes the alpha is so large that instead of going even in the right direction, we go completely in the wrong direction. We diverge. So that's a problem of a too high alpha or learning rate. So hopefully we have to figure out what is just right or optimal level of alpha. With the smallest number of iterations, we get to the point that the gradient is equal to 0. Okay, now the question is, why should we go beyond gradient descent, right? There are some important disadvantages of gradient descent that makes us wonder, can we do it even better? And the answer is yes. So what are the disadvantages? First of all, and I think this is one of the most important one, is that the gradient descent is single batch. So what it means that it's going to use the entire train set to update the parameter. So as I said in the previous slide, if I want to go from here to here, the gradient descent is going to apply the entire train set here at this point, right? So, and if the data set is large, each step is going to use the entire train set, and obviously it's going to be slow. The second problem that we just talked about is that it is sensitive to the learning rate, right? So finding that learning rate itself is going to be expensive. And obviously a combination of two is that it's going to be slow for large data sets, right? So what is the solution? The solution is something called a stochastic gradient descent, or in a more general term, mini batch gradient descent. So the idea is that mini batch gradient descent is that it's a version of the gradient descent algorithm that it speeds up the computation by approximating the gradients. So it's not going to calculate the exact gradient, which is based on the entire data set. It's going to use a subset of data sets and basically try to calculate the gradients based on the subset of the data set. So it's going to approximate the exact value of gradient, right? So using smaller batches. So this is the idea of mini batch stochastic gradient descent. So it means that in this iteration, let's say we're here, I'm not going to imagine your train set has 1 million observations. This is train. And in gradient descent, I'm going to use all the 1 million observations to get an update, go from here, to go from this theta to this theta. Now, in a stochastic gradient descent or in mini batch gradient descent, I'm not going to use 1 million. I'm going to use a batch of that, let's say 1,000. So I'm going to use 1,000 random observations from 1 million observations and then make an update. So this update is not going to be as accurate as the previous one because we're using fewer samples, obviously, but it's a good approximation of that gradient, right? So that's the whole point of batch gradient descent. So what is the difference between batch or maybe mini batch gradient descent and stochastic gradient descent? In mini batch gradient descent, the batch size is larger than 1. So obviously you have more than one observation, let's say 2, 10, 1,000 as in this example. In a stochastic gradient descent, the batch size, let me actually use a watercolor, the batch size is equal to 1. So this means that at each iteration, we are only using one random observations from the train set to update the parameters. As you can guess, it's going to be a lot faster, at the same time, a lot noisier. So let's see in the next slide, let's see how we can visualize this. And by the way, stochastic gradient descent has its own different upgrades. So we're gonna talk about it in the following slides. Okay, so here's the picture that I was referring to. It's a very intuitive one. Imagine this is our cost function, and we only have two parameters, and I don't know, you can call it theta 1, theta 2, theta 1, and this is our theta 2, right? And then this is the cost function. We can look at different contours, right? And visualize it like this. So obviously here is the minimum point. Let me use yellow, you see it. So this is the minimum point, and the goal is to get into that minimum point, right? The blue one is our batch gradient descent, and let's say the batch size is the entire train set. So I'm using the entire train set here. So I start from a random point. Let's say we start from this random point. And we use the entire train set. We find the right direction going down these counters, or going down the surface of the cost function. And because we're using the entire train set, this is going to be accurate approximation of the gradient, right? So we know the exact size and magnitude of the direction of the gradient, and we go along that direction, the opposite of that direction, right? Then we repeat this process, and as you can see, this batch gradient descent, or using the entire train set gradient descent, is going to be very stable because it is clear that at each point where direction should we go, because we're using the entire data set. The mini batch, let's say we start from here, I don't know, maybe we start from this point, it's going to be the less stable, but at the same time, it's not that awful because we're using, I don't know, maybe hundreds or thousands of the of this training set. So sometimes it goes in a, not necessarily the right direction. So here, look at that. It's going in the wrong direction actually, but it's going to fix it up quickly because again, these are better approximations of the gradient compared to purely a stochastic gradient descent. Eventually, we're going to get there, right? And then finally, for the stochastic gradient descent, let's say we start from here. The problem with that is even at the very first point, we can go in the wrong direction. And that's a problem because we're working with only one sample from the train set. So the bad news is that it's not going to be stable, but the good news is that it will get there. It will get there because, again, this is random sampling, and hopefully we get enough good random numbers down the road that can lead us to the optimal value for gradient, right? So what is the plus side? It's going to be super fast, super fast, because for each update, we only need one observation, and this is very key. Okay, all right, and as long as your cost function is continuous and differentiable, let's say it's well behaved, this stochastic gradient descent is going to work, right? And of course, but sometimes, again, in machine learning, the cost functions are usually well behaved, right? But in neural networks and deep learning, the cost functions are not as simple as this, right? So there are going to be, in the later parts in the course, we are going to visualize some of the cost functions in neural networks, and it's going to be super, super noisy. You know, this is something like that. It's a surface like this, and then you're trying to minimize over this. So for that, we need to go even beyond a stochastic gradient descent. Well, actually, here is, I brought the picture. You don't need to wait for the neural networks part of the course. So the idea is that why we should go even beyond this stochastic gradient descent is usually for deep learning. When the loss function is not necessarily well behaved, it's difficult to optimize. So here is a paper that visualized the loss landscape of neural networks, and as you can see, it is very, very noisy, right? And we have so many local minimums all around the place, and hopefully we are trying to get to this global minimum, right? So it's going to be difficult to get there because imagine, let me actually visualize it in two-dimensional space. Imagine we have something like this, right? And if I start from here, and if I use gradient descent, batch gradient descent, mini batch, or stochastic gradient descent, the algorithm will get stuck here because at this point the gradient is equal to 0, no update. If I start from here, the algorithm is going to get stuck here. If I'm lucky and it starts from here or here, I get to the global minimum. But how can we fix this? So the way to fix this is by designing an adaptive learning rate, right? So this learning rate should work in a way that it adapts to the loss landscape, right? So for example, it needs to incorporate the previous values of gradients as well, right? So we call this momentum. So rather than just looking at the current gradient, it needs to take into account the previous weights updates as well, right? So for example, if you're doing something like this, if the gradient is, I don't know, here's high, it's going to take larger steps, here's going to take smaller steps, but at the same time, it's going to take into account the previous weight updates. It's going to give this thing, imagine of it as a rolling ball down the hill, enough momentum to pass this local minimum and then go to the global minimum. So that's the idea at a very high level and in a very nutshell. So this is a point of what we call momentum, and it's a very effective way to for finding the global minimum in neural networks. So these extensions that using momentum, there are different versions of them, namely Atom, AdaDelta, AdaGrad, and RMS prop. So these are the more commonly used, especially the RMS prop and Atom when it comes to optimizing the loss function for neural networks. But for machine learning algorithm, usually the cost functions are very well behaved or compared to this ones, and the stochastic gradient descent should just work fine. All right, now I think we have all the moving part of this puzzle. Now we can put it together and see how do machines actually learn. So this is a very important part of this video. It's actually the last slide. I want you to pay very good attention. So what do we do? As a researcher, we have a research question in hand, we have some interesting hypotheses, we collect data, and we start to build a model and see how that model make predictions, right? So step one, we are going to actually, let me plot our black box. This is our machine learning thing. And there are some inputs. The inputs are X's and Y's. And if it is a supervised learning model, right? And I'm going to divide it into three parts. Train, test, split. If the data set, train, test, and validation. If the data set is small, we're going to do train tests and divide the train into using cross-validation, right? And then we are going to come up with a structure for the model. Depending on the type of the data, we use different architecture. So for example, if you're dealing with a structured data, we can do linear regression, we can do random forest, we can do XGBoost, we can do KNN, different machine learning models. If it is unstructured data, we know that we would be better off using neural networks or some deep learning models, right? So whatever it is, we are saying that, okay, this is the architecture of the model. It's a function of inputs and the parameters of the model. The parameters can be the weights, can be the hyperparameters, and etc. Okay. The next step is to initialize these values for parameters and hyperparameters, and we do it randomly. So random initialization. So we say, okay, W can be some random stuff, random numbers. The hyperparameters can be some random numbers. And then with that, let's go ahead and use a train set and start training the data, training the model, right? So how do we do that? By using these values, we're going to come up with some predictions, right? Because remember, we do have the weights now. It's a random number. Based on those weights, I can apply it, use the original data X, and come up with some predictions, Y hat, right? So we make predictions in a train set and validation set. And at this stage, we don't make prediction on the test set yet. It's too soon, right? Because we haven't optimized the model yet. So then we have these predictions, we have the actuals. With predictions and actual, we are going to look at some performance matrices, right? So for example, we look at MSE in regression, we look at accuracy in classification, and etc. Right? So we now have a sense of what is the performance of the model in the train set, in the validation set, right? So at this point, the model should perform very poorly because why? Because we started these weights randomly, right? So this is obviously not the answer to the model, right? So it's time to optimize those weights. How do we optimize those weights? We're going to use, again, if it is machine learning, well-behaved cost function, we can do gradient descent. If you want to speed it up, we can do a stochastic gradient descent. If it is giving you a hard time kind of functions, cost function, we have to use some more advanced solvers like Pedram or RMS prop, right? So, but in either case, at this point, I want you to pay attention. These happen simultaneously. This is step number 7. The optimizers, the solvers, update the parameters, these weights and these, let's say, just only the weights of the model using the train sets, right? So this is the learning part. This is what we call the model is learning something, is learning those weights, right? At the same time, pay attention here, we're updating the hyperparameters of the model using a validation set. And again, if the data set is small, using cross-validation or iterative cross-validation, k-fold cross-validation, right? But anyhow, at the end of this step, at the end of step 7, we have an optimized version of the weights here, right? So this is iteration number 1. So the weights have been updated, the hyperparameters, let me show them with D, have been updated as well. We're going to go through this process one more time, and then look at the performance. If you're happy, we move on to the next step. If you're not happy, we iterate through this thing, okay? Until we get to a point that we are satisfied with the performance of the model in the cross-validation set, right? After that, we go to the last step, which is, okay, let's go ahead and look at the performance of the model and see how we can deploy it in the wild world. And hopefully your model is generalizable. It means that it performs decently in a data that has never seen before, right? So this generalization is key. So the end goal of machine learning is to come up with a model that can generalize well, that can make predictions on the never seen data.
Okay, before we wrap up this section, I want to talk about a concept called feature scaling or scaling the features. By the way, by features, we mean the X variables in the data, right? Remember, in machine learning language, we call those X variables or explanatory variables the features. So when we say scaling the features, we're focusing on the right-hand side variables, the X's. And we're going to, in general, we do feature scaling because it helps in speeding up the training process, especially in algorithms that use gradient descent optimization. So now that you know what is gradient descent, you should understand this concept better. And this is particularly true, and it's important for algorithms that calculate something called distance between the data points, right? Those models can be like, k-nearest neighbors or k-means clusterings or things like that. So don't worry about these models. We're going to cover all of them later in the course. But remember, when it comes to those models that we need to calculate the distance between data points, then feature scaling is going to become important because by having features on a similar scale, the model can learn more fairly and accurately from the data, and it's going to become more efficient in terms of learning process. So let's see what is feature scaling. So why feature scaling? Feature scaling in machine learning is a critical step during the pre-processing of the data. And we do that even before creating a machine learning model itself, because it is essential for machine learning models that calculate the distance between the data. So for the models that for some reason we need to incorporate calculating the distance between observations, we end up scaling the features. So some examples for those models are like, KNN in supervised and k-mean clustering in unsupervised, principal component analysis. And later on, we're going to see that some other models that we ended up using gradient descent, and we will see feature scaling is going to become very, very beneficial when doing that. Okay. So in general, feature scaling could help the computer to avoid numerical overflows and speed up the algorithm, because computers in general have hard time handling super tiny numbers and from one hand, and also gigantic ones on the other hand, when it's come to calculating the gradients, right? And the feature scaling also helps us to reduce the dominance effects of a specific variable. So let's look at an example here. So imagine this is our loss function versus two parameters of the model. And we'll see that the gradient of larger parameters dominates the updates, right? So in this example, with different range of each features, and then this means a different range for the parameters themselves, the counters may be extremely skinny, which will make the gradient descent suffer from extremely slow numbers, right? So then what's the solution? We can, by doing scaling or normalizing the parameters, we can be sure that both parameters in this examples could be updated in equal proportions, right? And as you can see, the path to optimal is going to be a lot smoother when we have scaled the features, right? So in general, remember, if the model is somehow incorporating calculating the distance between observations from one hand, and also involves using gradient descent and its family in the optimization process, generally feature scaling is going to be helpful. Now let's see how we can scale the features. Well, the most common scaling practices are namely standardization and normalization. So standardization, which we are also familiar with the name of z-score, it's basically taking the average out and dividing it by the standard deviation of the random variable, right? So this is the way that we're going to make sure that we are standardizing our feature using this formula. And on the other hand, we have normalization, and for normalization, we can use either min-max scalar over range 0, 1, or we can do min-max scalar over range -1 and 1. Right, and the idea is very simple. For when you're doing min-max scalar over 0, 1 range, basically we take the random variable and subtract the minimum and divide it by the range. Right? And then this guarantees that the range is going to be between 0 and 1. So if you want to change the range from 0, 1 to -1 and 1, obviously you can multiply it by 2 and subtract 1 from each side, right? So this is going to be the formulas we use for normalization. Now let's look at an example. Imagine this is our original data, and these are the features, right? So let's say feature number 1, this is my x1, this is my x2, and x1 is between, let's say, 10 to 15, and x2 is between 0 and 10. This is a very simple example. In real world, the magnitudes are going to be a lot different, right? So for example, one variable is in percentage, the other one is in $1 million, and etc. Right? Now, I'm going to show you two pictures, and I want you to think about it, which one is doing the standardization and which one is doing the normalization. So let's start with the first one. So the one on the left, so what do you think is it? Is it standardization or normalization? So it seems that the range is, it can go from a negative number to positive number, and so this one seems to be what? The standardization. So we are taking this observation and using the formula of z-score. So this is going to be the new layout of the data, right? So this on the left is going to be our standardization, and on the right, this is going to be our normalization, right? And which one are we using? Min-max scalar over 0, 1 or -1, 1? Yes, we are using min-max scalar between 0, 1. So everything is going to be squeezed in that area. All right, now let's talk about normalization versus standardization. Well, the choice of using normalization or standardization will be totally depending on your problem and the machine learning algorithm that you're using. However, there are some rule of thumbs that we can use to figure out either you would be better off using standardization or normalization. So the first one is normalization is good to use when the distribution of the data does not follow a normal distribution. Guys, remember that normalization necessarily has nothing to do with normal distribution. It's, remember, one of the example was a mean max scalar, right? And if the data does not have normal distribution, maybe normalization is going to be a better fit. And secondly, standardization can be useful in the cases where the data has a normal distribution. However, this should not be necessarily the case. We can think of examples that the data is not normally distributed, but standardization is going to be helpful as well as normalization. And unlike normalization, the standardization does not have a bounding range. So this is really important because even if you have outliers in the data, then those outliers are not going to be affected by standardization. And more importantly, those outliers are not going to squeeze the data where the data is most concentrated, right? Because remember, in the normalization, the mean-max scalar, the denominator of the formula is affected by the range. And if you have a bunch of outliers from both ends, then the range is going to be hugely impacted by those outliers. Yes, the standard deviation is also impacted by outliers, but the effect is going to be more severe in normalization versus standardization. So whenever you have outliers and you don't want you don't want them to be affected by the normalizers, by the feature scalar necessarily, you would be better off using a standardization versus normalization. And as I said earlier, it really depends on the problem and the machine learning algorithm that you're working with to decide if you want to do normalization or standardization. Okay, now let's go over some general hints when scaling the data, right? So the first one is we should be careful when scaling the time series data. Why? Because as you know, when you're working with time series, if there's a structural change in the data, then scaling the time series would be misleading. So let me give you an example. Imagine you're talking about a growth company. At the earliest stage of the life of the company, maybe the fluctuations is a lot, but at some point, the company is experiencing an exponential growth, right? So maybe, yeah, we're talking about a successful company. After that exponential growth, and then both the volatility is going to be up and higher, and the magnitude is going to be a lot different. So for example, here we are talking about in terms of thousands of dollars, here are just tens of dollars, right? And then when we are trying to scale the data here, if you use the entire range, then the effect of these earlier years is going to be very tiny, which is kind of giving us a misleading representation of the data back then, right? So if there's a structural change in the data like this, then we should be careful. Maybe we should split the data into separate time series and then use the separate transformation to that part of the data. So that's one thing. Another thing is that in order to avoid data leakage, it is a good practice to fit the scalar on the training data and then use it to transform in the test data. So what do we mean by that? Remember, if this is your data set, let's say 80% train and 20% test, you're going to figure out what are the parameters of the scalar using the train set. So for example, if you're using the standardization, let's calculate the average and the standard deviation using the train set. And then when you have the formula, x minus mu divided by sigma, you can apply this mu and sigma from the train set and transform the test set data using this formula. So it is recommended to do it like this because you don't want it in some extreme cases, you don't want the very big outliers or leverage points in the test data affect your scalar, because at the end of the day, remember, in machine learning we want to test the performance of the model in the test set, and you want to make sure that there is no cheating going on. The model has not been trained in something that it has seen before, right? So standardization or scaling the features is also part of that process, so we should be careful about that one. Then remember, scaling does not change the shape of the distribution. So whatever the shape of your distribution is for any kind of random variable, it's going to remain the same. So if it is like this, it's going to remain like this, but only the scale is going to be different. Okay? And then finally, scaling is beneficial to most, not all, to most machine learning methods. However, remember, modern implementations are robust to features lying in different ranges, right? So, this point is somehow hinting to us that maybe there are some disadvantages to scaling the features, right? And more modern packages in Python or R are being developed in a way that you don't need to do this pre-processing step. You don't need to scale the features. You work with original data from scratch. Okay, that was it. This is our module number 4, Machine Learning Fundamentals. Okay, we did it in two parts. In part 1, we covered the fundamental concepts, and in part 2, we answered this question of how do machines actually learn. Hopefully now you have a better understanding of basically what's happening under the hood when it comes to machine learning. Because remember, in module 3, we talked about linear regression. In module 5, we are going to revisit linear regression, but now from another perspective, from machine learning perspective. So until the next one, take care. See you soon.